Always sensible to think about physical properties of a functional group or a molecule containing a particular functional group. So here is our standard carbonyl compound, dominated of course by that carbon-oxygen polar bond, and so as it's a polar molecule it will experience in the solid and the liquid states dipole-dipole forces. If we compare a series of organic compounds that have about the same molar mass, because of course remember molar mass has a significant effect on things like the boiling point. Butane, molar mass 58, boiling point -1. 1-butene, molar mass 56, boiling point of -6. Propanal, so here's our interesting aldehydes here, jumps up to 49 degrees C. Propanal is a structural isomer of acetone, so the 3-carbon containing ketone that's got a molar mass 58, obviously, if it's a structural isomer of propanal, and a boiling point of 56. And then we go to 1-propanol, an alcohol, same size, 60 as the molar mass, but the boiling point jumps up to 97 degrees C. And this is a lovely example of the effects of the different types of intermolecular forces. Butane, 1-butene, non-polar, so therefore they only have dispersion. Our carbonyl compounds, the aldehyde, propanal, the ketone, acetone, have got dipole-dipole forces. Dipole-dipole forces stronger than just pure dispersion forces, so they have the higher boiling points. Because dipole-dipole, nice as it is, there is no hydrogen bonding as there is in propanol, because of course for hydrogen bonding you not only need a very electronegative oxygen or fluorine or nitrogen in there, you need a bond to said very electronegative oxygen, nitrogen or fluorine. So our carbonyl compounds, their boiling points, their melting points, their heats of fusion and so on lie in between the pure dispersion alkanes and alkene hydrocarbon molecules, but not as good as those in which there is hydrogen bonding. However, if we think about the solubility of these species in water, obviously butane, 1-butene, just dispersion, negligible solubility in water because unlike does not dissolve unlike, if we cast back to that intermolecular forces chapter. However, when we get up to the propanal and particularly the acetone, we do see a significant solubility. 20 grams in 100 mils is not to be sniffed at. For comparison's sake, sodium chloride solubility, that one says, oh, very soluble, 35 grams in 100 mils. So propanal, nicely soluble in water. Acetone, miscible, in other words, completely soluble in water. And of course, propanal, completely soluble in water. Now, why this huge big jump here? And it's because while this carbon-oxygen double bond cannot involve itself with hydrogen bonding in the pure substance, as soon as you start mixing it up with water, this oxygen, very, very significantly slightly negative. It can't have a hydrogen bond with it itself, but it can make a hydrogen bond with something like water, in which it acts as a hydrogen bond acceptor. So physical properties, as you might expect, given that the compound has got dipole forces, it is a polar molecule, so it's got a higher boiling point, they have higher boiling points and so on than the equivalent hydrocarbons, but because they cannot hydrogen bond with each other like alcohols can, then they've got a much lower boiling point than that. However, they can hydrogen bond with water, thus are soluble in water.